Imagine this. You're playing a cartoonish racing game. You have your boost meter up in the top right corner. And when you mash the boost button, you go faster. If you deplete your boost meter, you'll have to go normal speed for a bit while you charge up again. We're building that game for real life. An electric drive system with a tiny battery and a gas-powered generator on board. All of the scary electric torque, none of the weight or range anxiety. The little battery is your boost meter, and the generator is what's refilling it, as well as providing you your base level of power for going normal speed. This is the first episode of that saga. Years ago, my buddy Vincent made a tiny generator from an old weed whacker engine and a brushed DC motor. Somehow, this wound up in my possession. I hooked up a microcontroller and some relays, and was able to stop and start it programmatically.
Voila!
I added a brushless motor as a simple load.
Sick.
And then an RC servo to run the throttle to increase the engine's power output as the drone motor sucked down more juice. I built a simple PID loop around it, and it worked pretty well. And then this happened. I put the project on a shelf for 6 months. I bought a crappy mountain bike off Craigslist, an e-bike conversion kit, a pile of lithium ion phosphate cells, and a battery controller. I took it for a ride on battery power alone and scared myself. Rather than doing the simple thing and replacing the broken motor and shaft coupling, I decided I'd start over, buy a commercially available 50cc 4-stroke motor and hook it up to a larger DC motor via a chain drive. The engine I bought had no output shaft, no machined locating features for output at all, just a casting with a couple of blind threaded holes where a centrifugal clutch was supposed to go. But the clutch was of no use to me because I wanted to be able to backdrive the engine to start it. It was impossible to get the shafts aligned and running true. Chains went flying, shafts broke. I got frustrated. I did get some footage of one run where it made power for a little while though, maybe averaging 250 or 275 watts. I went back to my safe space of computer programming and built a heads-up display for the battery controller, and it all went back on the shelf for another 6 months. Toward the end of 2024, a YouTuber that you probably also follow told me it was time to buy a 3D printer. So I did. I've been wanting to build an electric generator for a long time, so I started in on that quest. I started by winding some coils, at first by hand, and then with a stepper motor driven by a microcontroller to count the turns. I waved magnets at the coils, I lit up some LEDs, I drew lines on an oscilloscope. I hooked up resistors and felt around for some torque. I explored the design space and made predictions. I drew up and printed a prototype. As a side note, I also finally came to understand what magnetic reluctance is. I'm kind of embarrassed by this actually. It feels like something someone should have demonstrated to me when I was in about 3rd grade. I put some back iron on my prototype and saw about a 10% improvement in open circuit voltage. I got a little focused on P equals V squared over R, which led me to thicker copper wire, but also to double down on putting as many turns as possible on each coil. 2x the turns gets you a factor of 4 in the numerator in that equation, for only a factor of 2 in the denominator. Did I mention I wrote a replacement for the Arduino runtime on ATmega 328? That was fun. Someday I'll put that on GitHub. I made another attempt at putting a shaft on the weed whacker motor. This time, I thought I'd machine some locating features onto the flywheel first. So I made this tapered arbor to hold it, faced it off on the lathe, and then milled some flat edges onto the threaded bosses. These pockets locate against the bosses, and on the other side there's a shaft. It went okay, but like an idiot, I made it smaller than the smallest keyway I could broach. I made a 3rd attempt, but something went wrong while I was milling and the runout was even worse. I decided to abandon the weed whacker motor. There was no off-the-shelf 50cc four-stroke motor that I could find that had a proper output shaft. I looked over at a mini bike kit I bought a couple of years ago that's been sitting on the shelf. That's it, I told myself. This 1 kilowatt project is now a 5 kilowatt project. The Predator 212 is not only cheaper than a GX50 clone, it's got an output shaft on it already, and 5 times as much power. I designed a new, full-scale prototype. I 3D printed an enclosure, stator, a bunch of bobbins, and a lot of 3D printer support material. I wound 18 coils by hand. Frankly, this was pretty tedious, but it did give me a pretty good intuition for how the wire behaves when you're rolling it up. Here are some bobbins. This is what the whole stator assembly looks like. The rotors needed to be made in 2 parts, with separate hubs, because the outside diameter of the rotor was larger than I could fit in my arbor press to broach the keyway. I learned an interesting lesson while broaching my first keyway as well. I got a little overzealous with the circular saw rough cutting the stock, but overall it came together pretty well, even if the OD didn't entirely clean up. The second rotor came out better. The magnets are held with a 3D print that press fits into the rotor. I got it all piled up on the mill and it made a handful of watts. And if I crank this up, and now we're getting a few more. I cranked it up and let it make about 800 watts for a few minutes. Of course, I didn't film that. And then the PLA that the stator assembly was made of melted. The bobbins were sagging into the rotor. The smell of hot PLA permeated the air. Things were very warm to the touch. Disassembly revealed that all the bobbins were loose and warped. It would never be right again. Hours of work gone in a blaze of glory. And the whole thing went back on the shelf for another 4 months. Winding the coils by hand for that last prototype was pretty labor intensive and boring. I'm a software engineer, so the question is, why would I do something slow and tedious by hand that would take 2 or 3 evenings of what amounts to somewhat meditative manual work, when I could spend several months researching, buying parts, and building a machine to do it for me automatically? So I did just that. I bought some linear stages, a closed-loop stepper kit, an O-drive, some pneumatic cylinders, and a linear transducer. I got to be back in the comfort zone, inside at the computer, working on small electronics and programming. With all that integrated and working, the time had come for Vincent to head on down for a long weekend project sprint, and we built the winding machine. The days were long, the nights were late, and when we finally got it basically more or less working at some point past 2 in the morning on the second day, things got rowdy for a few minutes.
It's working.
So how does this thing work? Basically, it's a 3-axis CNC machine that just drags enameled wire around the stator poles. The key is a consistent tension on the wire, and that's what this thing does. It's an unspooling drive implemented with what's called a dancer pulley. The tension is controlled with a regulator feeding into a pneumatic cylinder, and the displacement is measured with a transducer. The microcontroller implements a PID loop feeding the measured displacement into a torque command for the O-drive. As long as the pneumatic cylinder isn't against its stops, the wire tension is proportional to the cylinder pressure. I futzed around for a few days to get the tensioning machine to work with the thicker wire. The key there was much larger pulleys. After that, I took a hard-earned retreat into computer land and wrote a program to generate G-code from a winding specification. I designed a new, small prototype motor for testing the winding machine, and eventually I was able to wind a stator with it. 3D printed the rest of the motor design for fit up and tested it.
ESC says it's good for 26 volts, so we're going to give it all the beans, as is customary.
It worked. I don't love 3D printed parts spinning fast though, so I rebuilt the rotating assembly out of aluminum. This time I added a feature to locate the magnet holder to ensure that the magnets were perfectly aligned between the two rotors. It took forever and the results weren't great. There was a bunch of run out and wobble. I suspected that the rotors were misshapen, but after rectifying that, I decided that most of the problem was the shaft. So I remade it, but out of frustration, I filmed nothing. After that, it worked better and I did some more sketchy run-ups. I wasn't entirely happy with the way the winding pattern on the first stator worked out. The runs of wire that go between the stator teeth all sort of ended up on one side. You can see that there are 3 here, 2 here, 1 here, and none here. I wanted to even that out. So I made some toolpath adjustments and wound another one with thin wire just as a test. It was basically what I wanted, so I went back to the thicker wire. There was a lot more futzing. One recurring issue from the beginning was that we were actually using a stainless steel straw as the wire guide. It's a 6mm OD with about a 0.5 mm wall thickness. I had been using a trombone bell-shaped 3D printed insert to guide and protect the wire as it comes out of the straw. The Germans probably have a single word for that. But we called this part the butthole. Without the butthole, the sharp edges of the straw would strip off the enamel of the wire as it came out. You can see the butthole give up right here, and then the enamel is damaged on the wire that comes out from then on. Keeping the butthole from tearing out had been a perennial struggle. Eventually, I found some kind of radiusing end mill and some appropriately sized stainless tube. It worked great. Butthole problem solved. I wound another small prototype stator, this time printed out of ABS so I could actually push some amps through it without it melting. I wanted to do something a little more torquey than just spinning a propeller, which meant I'd need to upgrade from the sensorless hobby ESC I'd been testing with. I took a crack at putting a rotary encoder on the motor, thinking I'd hook it up to the e-bike controller from earlier. I cooked up some microcontroller code to read the absolute angle data from the rotary encoder and generate an output that emulates the Hall sensor signals that the e-bike controller expects. Of course, I was really just wasting more time in my comfort zone of code and laptop. I gave up once I realized I'd need a whole mess of transistors to get it to actually talk to the e-bike controller. Maybe I'll come back to this later. I printed an ABS version of the full-size stator. The print took forever. It was way too floppy. I wanted to test my toolpath without wasting copper, so I wound a single phase out of fishing line. That worked, so I tried printing another design with a little more structure. Something went wrong on the first winding attempt though, and it broke basically immediately. I was sick of breaking 7+ hour prints. I redesigned it to be more modular so that if something broke mid-wind, I could tear it down and restart without having to throw the whole thing away. Weeks of futzing ensued. Progress was slow. I made hours and hours of footage that basically looks like this. Suffice to say, these particular coils were about the best ones I made. Ultimately, it required a lot of babysitting and manual interventions, and the result was just about the most labor-intensive A is for anarchy symbol you've ever seen. Vincent came over, and we built a minimum effort bracket to get the generator mounted on the Predator engine. We got it put together, and I looked at it and thought, why is this so bad? A bit of fresh gas and the motor ran again. Quick, plug it in and roll the camera before something breaks. We got a couple of runs in and both saw about 1100 watts for several seconds. The camera wasn't rolling on that run though. Here's a clip where it briefly did that. Then it broke. The shaft coupling walked off the generator's input shaft and then just sort of crashed back into it. We tore it down, futzed with it, tightened up tolerances, and put it back on the mill. It made about 600 watts at 4200 RPM. This project was kind of crazy. I am well aware of the many ways in which this thing is still pretty far from ideal, such as the story of linear problem solving, I suppose. Go ahead and roast me in the comments. My next move will be to parachute myself to another point on the design manifold and just keep descending that gradient. I'm going to put the rotors right on the output shaft of the engine. No separate shaft, no additional bearings. I'm going to rework the generator design to make better use of overall volume and magnetic flux. Probably get some physically larger magnets. I'll make the stator more rigid and reduce the number of winding layers so that the winding process is more stable. Bonus points if I can really get the wire routing dialed in and end up with some fixed terminal lugs on the exterior of the generator. After we blew the thing up on that last run, we woke up the next day and saw the perfect go-kart on Craigslist. 2 seats, some janky suspension, a blown motor. We picked it up and ordered one of those 10 kilowatt electric motorcycle power systems from China. If you don't want to see the outcome of that debacle, keep clear of the subscribe button.